You've got an hour, so you use it in whatever way you think best. These are aspects of iceberg mechanics.
Okay, thanks. Well, what I'd like to do is, being in front of a distinguished mathematical audience, run very quickly and lightly over all the unknown things about icebergs that there are, and which is a lot, and pointing out where iceberg research will benefit from the injection of some high quality mathematical modelling, and suggest maybe ways forward for iceberg mechanics research, and then end with a description of an experiment we did this summer, which also involved Till Wagner, and so we'll give a sort of dog and pony show at the end about that particular experiment, which did deal, well, it dealt with a lot of different things, but there was one aspect of iceberg mechanics that that our work was meant to cover, and we're still working on the results, of course. So I'll give a general description first about iceberg mechanics. Mainly, I was going to say I would recommend that you to buy my textbook called The Physics of Icebergs, written with a colleague in Newfoundland, which was due out this year, but isn't out yet on account of not being finished. But Elsevier is advertising it on Amazon already, on the grounds that its sales will be greatly increased by bringing it out in 2012, which is the 100th anniversary of the Titanic sinking, so that might increase its sales from maybe 10 to 20. But unfortunately, despite the fact that the cover is nicely produced and available on Amazon, the contents are not actually there yet. But they will be. Iceberg. This is thanks to everybody who was involved in the work this summer. And this was, which I'll come on to towards the end of the talk, this was the work that we were doing in Baffin Bay. And I was going to say, you probably seen the TV show, but if you haven't, we were working, the BBC Scotland invited us to do some work on an iceberg, a very gigantic tabular iceberg that was grounded in Baffin Bay. And the other scientists involved in that were a group from British Antarctic Survey, Keith Nichols and Paul Abrahamson, a group from St Andrews University that was doing mapping of the edges of the iceberg by multi-beam sonar, and Alan Stern from New York University, who was interested in the oceanographic structure around the iceberg. So there was some serious work done on that iceberg, despite the fact that if you see the film, it won't look as if there's anything serious involved at all. So, icebergs in general. First of all, there's two sources, the two different hemispheres. The most gigantic ones are in the Antarctic, and freshly carved Antarctic icebergs look extremely impressive. But when you actually go on top of them, they're simply, the part that you see is simply compressed snow, and so you can walk around freely as if you're on a snowfield, as long as you don't walk off the edge. And it is at the top, it's soft snow, as you can see from this. Unwisely, the Navy used a helicopter with wheels, so that sank in. So what you're dealing with when you're looking at Antarctic tabular icebergs, which look like very impressive masses of ice, is in fact a mass of snow. They're breaking off the Antarctic ice shelves surrounding the Antarctic continent, and so what you see when they break off is a cross section through the last few hundred or few thousand years of deposition of annual layering of snow, which gradually gets more compressed the further down you go. So right at the top, you can actually see the annual layers here. But as you move further down, it's compressed so much that you have to do a kind of averaging to work out which year corresponded to which depth below the surface. Also, the density increases with distance down through the iceberg, but you're still all the parts you can see of an Antarctic tabular iceberg are actually compressed snow or firn, which is where the crystals, the snow crystals, have freely percolating air or water between them, so that you're not dealing with ice officially. Ice officially is where you're dealing with a solid material with possibly air bubbles in it, but firn is a material which is granular, where there's still the possibility of air or water percolating between. So everything you see here is actually snow or firn.
What's the density compared with ice?
It starts at about 0.3 or 300, gets to about 800, which is when firn becomes ice at a density of about 800 kilograms per cubic meter, and pure ice is 920. So once you compress it to about 800, where you've got then the percolation is no longer possible. So you then have a solid material with air bubbles, and then you increase the density from there on.
And underwater, more or less the same size or much bigger?
And much bigger underwater. Here there's the main sources in the Antarctic are the large ice shelves, the Ross ice shelf, the Filchner ice shelf, but some sources are remarkably potent, like the Amory ice shelf gives rise to about an eighth of the iceberg emissions from Antarctica, despite being very narrow, because it drains a very rapidly flowing ice part of the Antarctic ice sheet. That's this portion over here. So there's the sources allow, especially the Ross and the Filchner ice shelves, because they're very wide regions covering deep continental shelf regions. As the icebergs break off, driven by various stresses, often swell-induced stress, you can get the possibility of very, very large icebergs being produced, but they don't survive getting outside the protective area of sea ice, which prevents them from actually turning, breaking up. So we have these cases of gigantic icebergs that have been produced in the last few years. This is sort of always, when there's a gigantic iceberg, it's always arouses a lot of publicity. This was one that came off the Ross ice shelf, and you can see this kind of gigantic battle went on. This iceberg, this is 10 kilometres, so this is over 100 kilometres long, one of the largest ever to carve, and it started drifting up the west side of the Ross Sea and collided with the Drygalski ice tongue and broke a piece of it off. The Drygalski ice tongue is a tongue of ice growing out from between two glaciers from the Antarctic ice sheet, and usually it's there protecting a bay north of that called Terranova Bay, which contains a coastal polynya, but the tongue was actually damaged by this iceberg hitting it. So you're dealing with some gigantic features there, but as soon as a feature like that gets out into the open Southern Ocean, it breaks up. And that's the Antarctic in a nutshell. The Arctic, the icebergs nearly all originate from the glaciers of East and West Greenland. So this is typical source regions. Mostly it's West Greenland and sometimes Baffin Island, with a few glaciers in East Greenland contributing. So the first icebergs that are produced are like Scoresby Sound in East Greenland. They have a very long trajectory. They move south in the East Greenland current, come around into the West Greenland current, are joined by lots more icebergs from the West Greenland glaciers, go up Baffin Bay, come round the top, and then come down southwards in the Baffin Island current, which turns into the Labrador current, and they end up off the Grand Banks, where they run aground and or melt, and that's the final latitude that they reach, somewhere down off the Grand Banks, which is where they do the damage to shipping. As they move south, they're constantly running aground because the Coriolis force is turning them to their right, so tending to run them aground. And so the numbers that actually get to different latitudes steadily diminish as you move south. So the numbers that reach the Grand Banks is a very small fraction of the number that enter Davis Strait, which is where the icebergs are being coming straight out of the Greenland glaciers. The numbers also are very variable from year to year, and this hasn't got recent years in, but there's been an increase in recent years because of a speeding up of the glacier flow in many of the Greenland glaciers, which is thought to be due to the fact that the Greenland ice sheet is showing surface melt now in summer, and much of that meltwater is going down to lubricate the bottom of the ice sheet down features called moulins, which are holes in the ice sheet, and that water seems to be a cause for acceleration of the flow of the Greenland glaciers. Sometimes they're moving about 2 or 3 times as fast as they were a couple of decades ago, and that's producing a big increase in iceberg fluxes coming out of Greenland. The final resting place is the Grand Banks, and the International Ice Patrol maintains a watch on all icebergs in the Grand Banks and where they're likely to affect shipping. And the absolute limit here, this was the iceberg that sank the Titanic, was actually about here. So it was really right on the limit of where you find icebergs. And when icebergs reach those latitudes, they're very, very much diminished. They've melted a lot, and they don't look very formidable, but they're still perfectly capable of sinking a ship, of course. There's been a few observations of outliers, icebergs. These are the normal outer limits of iceberg occurrence in the Arctic, but there's been some observations in places you don't expect to see them. In fact, there was one off Bermuda, and the question is, where do these come from? I mean, one source is the fevered imagination of drunken mariners. The second possibility is cold core eddies, because you can get cold core eddies coming from the Gulf in this case it wouldn't be off the Gulf Stream, because the Gulf Stream is the icebergs aren't getting as far as the Gulf Stream, but possibly coming down around down in the East Greenland currents, you can get icebergs caught in cold core eddies which come off, and this might explain some of the extreme values, but other extreme values are really too far away for that, and you have to kind of somebody should be looking very closely at each of these observations to see if any weight can be attached to them. But interestingly, you have the opposite phenomenon in the Southern Ocean, that at the beginning of this century, all the charts of the Southern Ocean were littered with islands that didn't really exist, and what was happening was sailors were spotting large icebergs, especially dirty icebergs, where dirt had fallen on the iceberg as it flowed out through the transantarctic mountains, for instance. And they said, "Oh, I've seen an island," and it was put on the chart for safety, and somebody had to go along afterwards and show that it didn't exist. So there was icebergs mistaken for islands in the Southern Ocean, but in the North Atlantic, there's icebergs which possibly didn't exist at all. The nature of the Arctic bergs is usually different. Antarctic bergs typically are tabular because of the sources being the wide ice shelves. There's only a few places in the Arctic where you can get sources like that. One of them is the Humboldt Glacier in northwest Greenland, which you can see is a wide apron which can produce and does produce tabular icebergs. And here you can see very much a mechanism which looks as if it could be swell-induced flexure that's breaking off the icebergs in strips.
What's the scale here?
This is with down here we're looking at about 100 meters, 100 to 200 meters as the diameter of those bergs. But the more usual source are narrow, fast-flowing glaciers flowing down between the mountains which fringe Greenland. So this is a typical iceberg-producing glacier. And here you have the whole science of glacier mechanics comes into describing what the icebergs look like. You can see that because the flow of ice is governed by Glen's flow law, which is that the strain rate is proportional to the cube of the stress, it's like it's creeping basically. It's like a kind of lump of blancmange sticking on top of the of the Greenland continent, Greenland land, and flowing outwards so that you have boundary layers both to the side of the glacier and at the bottom, and you have some questionable amount of bottom of of sliding on the bedrock, which has seemingly increased recently because of the lubrication from meltwater. But the stress fields produced by the boundaries at the top and the sides tends to produce these patterns of crevasses along the edges of the ice of the glacier and towards the ends of the glacier. So when that glacier reaches the sea and icebergs carve off, the iceberg's already equipped with a big pattern of crevasses, which gives them a lot of weak points, tending to make them break up more after they've been launched and started to drift. So a typical Arctic iceberg looks more like this, which is they're more dramatic and attractive to look at than Antarctic bergs because of this source being fast-flowing glaciers, which tend to produce these icebergs tumbling off the end into the sea and capsizing a number of times because of their random shape and breaking pieces off, breaking off because of crevasses. So typically it will end up looking a bit like this, and you can see this one, for instance, has capsized because this scalloping pattern here, which comes from small-scale convection of about lumps of this sort of size. You have this sort of scallop pattern. Is a sign that this used to be underwater, and this pattern is just incidentally is a potential kind of killer for tomography. Walter Munch has a plan to do tomography under the Antarctic, under the Ross Ice Shelf in Antarctica, but tomography requires sound scattering from a very smooth surface. That sound reflection has to be, you have to have a very flat surface. If the bottom of the ice shelf is made of this kind of pattern, that's enough roughness to kind of do in tomography as a method. So there's a real question of what the small scale roughness of the ice underside is under Antarctic ice shelves, and this is relevant to the applicability of tomography. So typically then you have these kind of capsizings that go on.
Tomography is acoustic.
Acoustic tomography, yes. And a first question in iceberg mechanics is what's the limit to the ice draft? When you look at typical distributions of Arctic icebergs, you see there's usually a correlation between length and draft, but the draft reaches a limit of about 230 meters.
Sorry, what do you mean by draft? Is that
That's
the depth?
the maximum, yes, maximum draft, but depth below the waterline. So you can work out the draft by looking at grounded icebergs, because you know that the draft is the water depth, and so the correlation is quite good until you get to some draft limit of about 230 meters, and this is thought to be the maximum draft of an Arctic iceberg, because 230 meters also is the deepest draft of the sills of fjords in Greenland that are iceberg producing fjords. So very often fjord is quite deep in its interior, maybe 600-700 meters, but you usually have a sill at the mouth of the fjord, which is a terminal moraine from from when you had the ice sheet being further advanced. And this means that icebergs are produced by the glacier that's in the fiord, or the glaciers, but they pile up inside the fiord and they can't get out because their draft is greater than the depth of the sill. So they sit there until they've melted enough to be able to drift out. So this gives you this 230-meter draft limit. But the trouble with this is that when people started to study iceberg scouring on the coast of Labrador, they were finding scouring out to water depths of 450 meters. And these were recent scours as well, not archaic scours from the last ice age. So somehow or other, there are deeper draft icebergs that are coming down the coast of Labrador. So the two questions, well, a question that was examined but maybe not examined enough, was how much can an iceberg increase its draft by capsizing? Typically, icebergs of a random shape will lose stability by pieces breaking off them. They will then capsize to give a different above water shape, and the deepest submerged sort of prong of the iceberg might have a greater draft than the original berg, and so an iceberg can increase its draft by capsizing. But all the models that were done only gave a few percent as the maximum gain in draft, so you couldn't explain these deep draft bergs that way. And what we suspect now is that there are iceberg producing glaciers that actually don't have sills or have deep sills, and that some of the icebergs are coming from those. There seem to be one or two in southeast Greenland, and it's simply that they weren't surveyed, because the surveying in the Arctic is not as advanced as surveying around in more civilized places. So there were some fjords had not been surveyed. So that's potentially solves this one iceberg mechanics problem, which is how do you get deep draft icebergs starting with shallow draft icebergs. There are a few icebergs within the Arctic basin itself. Nearly all of the icebergs that you see coming in the important areas of Newfoundland, Labrador, come from the Greenland glaciers, but there's one or two sources of icebergs amongst the Russian Arctic islands which carve into the Arctic Ocean and then come round through Fram Strait in the transpolar drift and then join the rest. And these are very rare, but by Murphy's law, even though there's a very small number of them, if you're in a submarine, you tend to hit them. And this shows a case where we were in a submarine and hit one. The thing is that when you operate in submarines in the Arctic, which we've been doing for many years to measure ice draft, sea ice draft, you run at a depth which is safe enough to avoid all the pressure ridges, which is about 50 to 60 meters. So if you run below that, you can get good resolution data without any danger of hitting a pressure ridge. But there are these very small number of icebergs, and they have deeper draft. So statistically, your chances of hitting one are infinitesimal. So this shows the limits of statistics, because here's a case where we actually ran into one. This shows the track of the submarine as we investigated around the edge of that thing, and then this shows this is the upward-looking sonar record, and this is a side-scan sonar record, and this is the iceberg. So this is just a little sequence that shows this is a forward-looking sonar that warns you of the iceberg up ahead. That's the big brown blob, and here's the iceberg seen by the side scan at different points as we go around it. That's a pressure ridge, and then this is the iceberg itself, which is...
What's a pressure ridge?
A pressure ridge is produced by, it's a sea ice feature produced by the normal sea ice, which is maybe 1.5 meters thick if it's first year, or 3 meters if it's multi-year, it being opened by crack forming, and then the edge is pushed together by the wind. So it's a kind of a piled up, a linear pile of deformed ice, and it can be as deep as 50 meters, but not really deeper. Statistically, probability falls away. So you don't get deep pressure ridges, but you do. But any iceberg is likely to be deeper than the pressure ridge. So this shows an Arctic Ocean iceberg. And what we think it is something like this. This is photographed from the air in Fram Strait, and it's a small iceberg produced in the Russian Arctic islands coming out through Fram Strait. So one of those, whilst it was still in the Arctic, was responsible for this mayhem that committed to this submarine. Then looking at, I'll briefly review other properties of the iceberg so we can get on to the work that we were doing this summer. Trajectories, iceberg drift, there's some very well worked out theory now of sea ice drift, which the driving forces are wind stress, current stress, Coriolis force, and internal stresses between ice flows and sea surface tilt. You can get make quite good predictions of sea ice motion, but when you apply the same model to iceberg motion, it doesn't usually work so well, because icebergs have these weird shapes, and so they're kind of sailing. It's like these jellyfish that sail at an angle to the wind. They're sailing at an angle to the current and to the wind because of their obscure shapes. And because their shapes are so different, you can't get a good theory that predicts iceberg motion except in general terms. So, for instance, the general picture is that icebergs from the Antarctic will end up drifting with the Antarctic circumpolar current, but it takes them a while to escape from the Antarctic continent because they're caught initially in the Antarctic coastal current and move westwards, and then because relatively speaking the Coriolis force is stronger on an iceberg than on sea ice, they tend to turn more to the left of the wind in the Antarctic, more to the right of the wind in the Arctic. So they tend to bump along the coast a lot until they reach some point where, for instance, a bottom feature like the Kerguelen Plateau allows the current to divert out northwards. Then they can inject themselves into the circumpolar current, and they tend to drift northwards because of this, in a sort of crabwise fashion, relative to the sea ice in the circumpolar current because of this Coriolis effect. And so you tend to see icebergs at lower latitudes in the Antarctic than the sea ice itself.
What's the typical speed of drift?
Well, here's some satellite tracking. So this would be about 5 to 10 kilometers a day. But sometimes they will run aground and stay aground for months or years, and then start moving again. So this is an iceberg that took 11 years to get from here to here, because it spent a lot of that time aground on different points along the way. Then, because they're moving differently from the sea ice, if you have icebergs embedded in sea ice, they will tend to carve out tracks for themselves through the sea ice. This is in Nares Strait. But there's another question, which is to what extent is iceberg motion controlled by sea ice? Because, for instance, the icebergs that are emitted from Baffin Bay and reach Labrador Sea tend to occur in seasonal bursts, which implies that at other times of year the sea ice in Baffin Bay is holding back the icebergs from where they would like to come down south. So
in clear water without the sea ice, what would be a typical relative speed between iceberg and water?
It would be maybe half a knot to a knot. It's small. It's a fairly small differential. The modelling is something which hasn't gone forward very much, but ought to have done. The trajectory modelling uses these kind of cast-off sea ice free drift models, but Garrett, the best advance was by Garrett at Dalhousie, who came up with a statistical model. He said, well, because you have the iceberg a random shape and tend to sail through the ocean instead of drifting in the way they should do, why don't we do an iceberg specific model where you put a couple of parameters in the equation for the sort of roughness and shape factors for the below water and above water part of the iceberg. You don't know what those are, but you optimize them by tracking an iceberg for about 48 hours, and then you have the free drift model with these unknown parameters, and then you optimize the parameters by doing 48 hours of tracking. Then you can put those parameters in, then you can predict where it will go after that. This is applied to icebergs in that actually tend to be emitted near drilling rigs, and it becomes an important problem because there's a lot of oil drilling going on in Labrador Sea and in Baffin Bay now, and iceberg trajectories are typically very looped anyway because of inertial motion, and then you add to that the random effect of the shape factor, means that that you don't know easily whether an iceberg that's seeming to bear down on a drilling rig is actually going to hit it or not. You need a better model to predict where that iceberg is going to go. So Garrett was recommending this as an improved iceberg model. And in fact, tests of his model against the sort of standard model show that it gives much better quality predictions, lower errors after 12 hours of modelling once you've established these parameters. So I think that is a real advance, but it hasn't been published except in a newsletter that I used to edit, and I suspect that Garrett has been using in consultation with the oil industry and applying this model to oil industry needs, and so it hasn't appeared in the literature yet. So now we come on to the question of breakup of icebergs, and which is what we were trying to do in our experiments this summer. And they depend on, first of all, this fact that tabular icebergs are compressed snow. So if we look at the typical density profile through the ice shelves which give rise to these icebergs, you've got snow of density maybe 0.4, or that's 400 now, at the surface, increasing in density as you get down through the iceberg because of compression of the snow by layers on top. It reaches this cut-off point of 800, which is where it turns officially into ice, typically round about 50 meters from the top of the iceberg, and then it's ice from then on. Now the trouble is that 50 meters also is typically the freeboard of an iceberg, an Antarctic iceberg, because they're typically 200 to 300 meters thick. So the 50 meters is because of the density variation, 50 meters is what you see above the surface. So everything you see above the surface is actually compressed snow, and at the waterline, which is where waves can erode the iceberg away, you've still got compressed snow just about, rather than real ice. So we have a mechanism whereby at the waterline you can get a lot of erosion going on due to simply melting and enhanced by wave action. So this shows a tabular iceberg, and you can see this wave cut at the waterline, which is a kind of universal thing with icebergs. This shows another mechanism of erosion of an iceberg, but I just mention it because it's due to the creep properties of the iceberg, and this was a mechanism worked out by Niels Ree in Copenhagen, and it's simply that if you have a tabular iceberg 200 to 300 meters thick, sitting there, and it's creeping, it will creep under its own weight, and the edges will start to flop over, and that will produce crevasses you can see here, you can see the curvature of the surface here. This was flat in the original, when it was originally part of the ice shelf, and you can see the annual layering is giving you bending over at the edge because of the creep of the ice, and that's leading to the opening of crevasses, and then these bits will fall off. So there's bits falling off the edge of tabular icebergs because of this re-type carving phenomenon. But you tend to get much more extreme erosion of the above water part, which is simply due to waves eroding at the waterline, a wave cut, and then the part above water just collapses because it's unsupported. So you then end up with an iceberg which is a coherent mass below the waterline, but has a bunch of isolated lumps above the waterline, looking a bit like Stonehenge. And these are called dry dock icebergs because very often in the centre of this is you think open water, but in fact if you tried sailing in there you'd run aground because it's a single iceberg here. It's a coherent mass of solid ice below the waterline. The parts above water have been eroded away by waves and successive collapses, but in the middle here this is very shallow water because the iceberg starts underneath this bit here. So these are called dry dock icebergs. And so that's the first thing is the erosion at the waterline. Then there's the question of how strong is the iceberg, how much of its original temperature does it retain when it gets into lower latitudes. Typically profiles through ice shelves in Antarctica, for instance, will give you temperatures of about -18 in the interior of an ice shelf. And when you look at icebergs that are recently carved, they've warmed up near the surface, the uppermost 10 meters, but when you extrapolate back down, it looks as if there's a cold core of underwater part of the iceberg which remains at a very low temperature. And the question is, how far does that cold core go? And some very brave people off Newfoundland started getting onto icebergs and trying to drill through icebergs near their southernmost limits. And there were various accidents. The icebergs were capsizing all the time and the people getting thrown in the sea. So these data were obtained at great cost, not at the cost of lives, but the cost of danger. And they were finding that, surprisingly, even at the latitude of Newfoundland, you didn't have to go very far down into the icebergs before you were finding low temperatures. Here's a berg that was at -13, only 2 meters in. And these other bergs were clearly heading towards low temperatures if they could have drilled further before the iceberg capsized. So there's the cold core in the underwater part of an iceberg remains right down to quite low latitude, and you can model how the heat flow from an iceberg goes, and it tends to get smaller by melting, but the iceberg that remains cold. So you have quite strong, in terms of mechanical strength, an iceberg retains a lot of mechanical strength underwater. Fortunately, I'm running out of time here, so I won't go into this very difficult question of modelling iceberg sidewall decay, and I'll refer you instead to Herbert Huppert, who did a lot of the basic research on this question, and here is his nice picture, which is hanging in Pavilion B, Pavilion H in Dampt, which was an experiment that he did on a melting vertical ice wall. This is vertical ice wall in stratified water, and finding a staircase structure of near the ice wall. And what's happening here is that as here's a brief summary of this. If you have an iceberg drifting into warmer water, you have an interesting problem where you have a vertical wall of melting ice water of some variable property, sort of stratification of temperature and salinity, and the fact that the diffusivity of heat and salt are different mean that you can get a variety of patterns of melt involving vertical motion up against the wall of the iceberg, or systematic set of layers, which have been observed in these nice cold room experiments, but have only been observed in one place in nature. That's off an ice isle, off an ice tongue in Antarctica. But that's not for want of trying, and we did try. My colleagues were working on this in this year and trying to release dye against the vertical wall of an iceberg.
What sets the scale of these?
Well, this is in the laboratory, so
Yes.
scaled up, it comes to about typically 20 meters is the typical size of the stairs.
I mean, what determines this wavelength?
Well, it's the level of it's the temperature of the water, the level of stratification of temperature and salinity. Those are the parameters involved, and there's a lot of interesting theory there, but the problem is we have very little data in the field, and because it's so hard to get up against the face of an iceberg and do anything. So we tend to use very crude parameterizations for side wall melt. This is the crudest there is in the world, a linear one. You get melt as well, but as well icebergs break up, and the breakup was what we were working on this summer. And the reason why it's very clear you're getting breakup is because if you look at the distribution diameters of icebergs, of tabular icebergs in the open Southern Ocean, they tend to be all smaller than about 1 kilometre, whereas at the source, where they were released, you can get giant icebergs. So something is causing them to break up. And the theory of breakup of or flexural response of a floating raft to waves is something which we developed about 30 years ago in relation to ice flows, because a very important problem then and now is the development of the marginal ice zone. That's the edge of the Arctic and Antarctic ice cover, where the ice is broken up into smaller fragments, flows by wave action, and that increases the melt rate. That was something that was studied very intensively from Cambridge and other places in the 1980s, and it's come back in as a new study. We're working on this with the Office for Naval Research because it's thought to be one of the mechanisms explaining the very rapid retreat of the summer ice in the Arctic Ocean. That because it's retreated much further than it used to, you're creating open water in the Beaufort Sea now in the summer, and that's producing this marginal ice zone which breaks up the ice even more. So you need to understand how the ice is broken up by waves. So we need to look at this breakup phenomenon. And the models of flexural response of an iceberg to waves and the flexural response of an ice flow to waves, which was the origin, tend to give you a set of allowable sizes for an iceberg. If you start out from smallest possible length and look at the strain field, the flexural strain field produced by a given wave height, here's two possible long period swells, then as the iceberg gets larger, you get more and more flexure until you reach a peak, and then beyond that there's the sort of resonance effect means that the iceberg responds less, and you can have then a larger size iceberg which in principle could survive if the stress is enough to cause it to break up somewhere in this slope region here, where you're increasing the strain as you increase the size. Somewhere a storm will produce a breakup to to a size given by a point on this part of the curve. If an iceberg is big enough to be in one of these regions, it might survive, but in fact, because the icebergs are rotating all the time, it will present another face to the waves, which will ensure breakup. So really,
The wavelength is in the range of 100, 200 meters.
yes, typical swell. Well, the swells that do the worst are the longer ones. So that's maybe 300 meters. So, but 100 to 200 as well. So this brings us on to finally to that about what we did this summer, and I'll ask Till to help here as well. And that we were working because of this interest and this new interest we've got now back again in breakup of icebergs, a breakup of floating rafts due to waves. We had the opportunity to actually measure a giant iceberg which had come off the Petermann Glacier in this is up here, northwest Greenland. There's a glacier which has accelerated in recent years and is giving rise to very large tabular icebergs. And one broke off 3 years ago, came down the east coast of Baffin Island and ran aground up here at 70 North. And there's been aground for the last year. The Canadians did some work on it a year ago when it first ran aground, and then the BBC decided to send some presenters and some scientists onto it to film what an iceberg is like and to give the scientists a chance to do some work. So we were happy to accept that and sailed out from Ilulissat to do that work. That's Ilulissat on West Greenland. This is the Petermann Glacier, and it's been calving again recently. It's accelerated and is producing these very large but tabular bergs, and it produced another load of another set of tabular bergs this summer. So it's really becoming a very productive glacier, and this is what the iceberg looks like or looked like this summer. It's 42 square kilometers. It's quite thin. It's only 75 meters thick on average, but that still gives you 3 billion cubic meters. That's 3 billion tons of ice there. And it was grounded off the Baffin Island shelf in about 100 meters of water. And so it's fairly formidable, and it looks, this is what it looks like from the side, and you can see the underwater part is indicating that there's some ice further out than this vertical face. So in other words, an unsubmerged ram all around the edge of the iceberg. And here's the iceberg itself. And when this is the topography of the Baffin Island shelf, and we found that it was not only grounded, but it was pivoting at a point, because the group from St Andrews University, which was, whenever the ship which was chartered sailed around the iceberg, they would be able to map the vertical faces of the iceberg with multi-beam sonar for underwater and laser for above water, and found each time they did it, it was adopting a different posture. So it was pivoted on a point near its northern end and was rotating with the tides and currents. But eventually, just as we were about to leave, or just as we were leaving, it came adrift and started to drift actually in towards the coast, but has now moved on. And so we were trying to work on the berg. Problems were that it was inhabited by polar bears, not penguins, and that made work difficult. The other difficulty was that the BBC, in its wisdom, had chartered they chartered a ship that didn't have a helicopter deck, so you couldn't get onto the iceberg safely by any means, because you really wanted to get on from the helicopter, and instead we had to moor to the iceberg and step onto the iceberg from the gangway, which is not a safe procedure. So instead of being able to put instrumentation all over the iceberg with a helicopter, which couldn't come in because of fog, we had to just put instrumentation around the edges, because you couldn't get very far into the iceberg because of, firstly, crevasses, and secondly, polar bears. So we were looking at edge effects instead of looking at flexion of the entire iceberg. But we used instruments like these tilt meters, which measure the tilt of the iceberg, and we had a wave rider buoy, which was continually mapping the wave field near the iceberg, which was entirely and always a swell coming in from the North Atlantic of about 10 to 12 seconds period. And this was the tilt meter was actually showing that the iceberg was responding to this swell, and this is the tilt response of the iceberg to the incoming swell, and it's got a peak of about 10 seconds. So the iceberg really was, even though it was 42 square kilometres, it was responding to this incoming swell from the ocean. Then we had an event which involved breakup, and
Tilt is simply
yeah.
from the vertical.
Yes, tilt from the vertical. Yeah.
It's not deforming.
No, and we couldn't tell whether it was flexing because we needed arrays of tilt meters to get that, and we didn't. We were only able to put the individual ones out. But while Till and I were standing on the iceberg one day, it broke up, and a piece came off. And this, luckily, there was we had a GPS recorder out at the time, and this shows the red here is the vertical elevation of the recorder, and then at the moment that the iceberg broke off, it leapt up by about 60 centimeters, and the original shape here, this is modelled by Pedro Lozagui in Spain, been working with us on this. It was simply moving up and down in response to the tidal variation, but then this was a sudden response here. And you can see there's things we're looking at the data. We've only really started to look at the data, and there were a couple of precursors, some interesting motions here which suggested that cracks were developing, which then suddenly turned into a calving event. And that calving event didn't seem to correspond to a period of exceptional wave activity. It happened when the wave energy was fairly moderate. This is a significant wave height at the time, recorded by the wave rider buoy, and this was the significant wave period. So the swell was just really doing its thing. It seemed to be fairly steady swell throughout the experiment. So there wasn't anything exceptional. It wasn't that could have caused that by itself. So what we think happened, but we're not sure, and I'll ask Till to say something about this, is that the piece that broke off, which is 40 which is 100 meters or 80 meters actually by 400 meters, as mapped here, photographed here and mapped here by the sonar. That piece, which was over here, it looks like what we see when I showed that earlier picture of the Humboldt Glacier, a swell-induced breakup event caused by the flexural stress reaching a maximum at a certain distance in from the edge of typically 100 meters or so. So if it had been pure swell coming in doing this, you could understand this in terms of wave-induced flexure theory. And so that would be, a nice clean picture. But first of all, it wasn't an exceptional swell, it was just an ordinary day. And secondly, we could see when we were looking in detail at what was going on, that there's another potential mechanism there concerned with buoyancy forces. And this is because when you look at the structure of the water column around, there was a CTD survey, and I'll just flip through that. It was showing that the water, typically the water temperature was near freezing point, but with a warm layer down to about 20 meters, that was because it was summer and you were getting solar heating. And so you had a sort of some kind of heat at the surface. And in this case, the iceberg, if we superimpose the iceberg on that, the picture we form, which is very dubious, well, not dubious, but preliminary, is that we could see this wave cut all the way around, and that wave cut was eroded by wave action, enhanced by the warmth of the surface water, cuts away the waves, cuts away the ice at the waterline. The unsupported part above the surface collapses, and we were constantly seeing that happening all around the iceberg, which made it very dangerous to get onto the iceberg. So an overhanging section breaks off. The wave cut goes further in, another overlapping section breaks off. In the meantime, by doing that, you're generating an underwater ram which has got a buoyancy force. That piece of ice would like to rise to the surface but can't. So you've got a lever arm here where the underwater ram is trying to surface, and that's producing stresses on the nearby parts of the iceberg, which would tend to produce zones of weakness, where if there's an existing crack, it might break, or if there's wave action, that might be where it would break it. So what we have to do is to do a full analysis of the stress field associated with underwater rams, and what kind of stress field is produced in the iceberg, where is the maximum stress at the top and the bottom, what is the can we predict the distance in that breakup will happen, and does it correspond with what we actually saw? And that's our current work in trying to interpret all of this. And when it does break off, this you will get a new iceberg fragment, which we got. And typically, its shape will be different because of the way it's broken off and the way that the shape contains a piece of the original ram. And in fact, fortuitously, we did see somewhere near the iceberg a piece of berg that looked just like what you'd expect from a breakup of an edge part of an iceberg, where the underwater ram has taken up this shape, and then as soon as you release the buoyancy, it takes up a new shape with two peaks. And so possibly fortuitously, here was a piece of berg that had looked like that and had maybe broken off in the same way. So this underwater ram, this is shown by this multi-beam sonar, seems to be an important element here, and so there's superimposed is this iceberg, the way it was after it broken out, and the way it may have been before that breakup happened. So the theory of wave-induced wave cuts goes back a long way. This is actually from a work in the 1960s by Stan Patterson, but it hasn't been observed kind of in action so much or at all, really. So it was quite lucky that we were able to, by default, expose ourselves to this extremely stupid risk of standing around on the edges of an iceberg that's melting and breaking up and observe it breaking up. Well, that wasn't the intention. The intention was to stand safely in the centre of the iceberg next to the helicopter as you put out beautiful arrays of instrumentation. But this is what ended up happening, but it did produce some data which we can test these models of how the edge, how the iceberg actually loses mass around the edges.
I think you said everything. Yeah. So I was until and I was involved in the experiment, and I did quite a lot of the legwork for collecting the GPS data and getting everything set up. And I think we were really lucky in a way that we measured the breakup and got away alive. That was sort of, I think that's sort of the summary. But it was, it was somewhat unexpected to have this very consistent, huge underwater ram all around the berg, and it did seem. I mean, we were right moored on that ram, right, and we actually felt as the berg broke up, we actually felt it hit the bottom of the ship. The ship sort of moved away a little bit, and we had to send the divers down to check whether the hull was okay. So it was definitely exciting, and it was scientifically.
You were on the part that broke off?
Yeah, Peter and I were standing just as where you see that jump in the red data.
Yes, that jump.
That jump was
up.
So we put the buoy right on the edge of the berg, and as you see, it sort of tilts up, and that's essentially what happened when those 60 centimeters came up. And we were standing right where that red line is. We were just there, and I was downloading the data, and everyone was like, "Oh my God, you've got to get on the berg!" And I was like, "Oh my God, I'm downloading the data. Give me 10 seconds." Felt like it felt like an action film. And we got it. Yeah, we got the data back. So
But BBC wasn't filming just then, was it?
they were, and it's part of the show. Actually, it does appear briefly, where we're all sort of scrambling back onto the ship.
Yeah.
Great program.
Yeah.
So if you wanted to sort of find out more, the thing would be to talk to Till and also have a look at the program, which having been involved, some of it makes us kind of squirm. It makes you realise how inventive the BBC is, and that is how little it resembles reality. But there is some film of the iceberg itself and the work we're doing and what it looks like and what was happening. So that is something. Maybe we've got the tape, so maybe we can arrange a showing of that.
Just show a bit of it anyway.
What do polar bears eat there?
The people.
No English sign.
Well, the thing was that the sea ice had been around that iceberg and then had retreated further north. So up until maybe June, the polar bears could freely come and go. And then as the sea ice retreated north, they were isolated, and they had to kind of choose to stay on the iceberg or to sit on the ice floes as they retreated. And we don't know exactly how many were on the iceberg, but wherever we stopped, there seemed to be one sitting there waiting to eat us. And they couldn't get any food because they were and so they would tend to patrol close to the edge of the iceberg, and that
They couldn't jump off?
one of them did look as if it was going to leap into the sea. There were some people out in a Zodiac, and the bear must have thought this would make a good meal. So he was on the edge, like somebody about to dive off the high board in a swimming pool, but sort of afraid to do it, and he didn't do it. But there's some nice film in the TV program of a polar bear kind of wondering whether he should leap.
So they're doomed unless some other scientists come to feed them?
Well, they can last several months. In fact, they often last several months without eating. And also they were swimming around. They would jump. They were somehow getting into the sea because we saw one in the water. So there would have been a shallow part of the iceberg where they could get into the sea, and then they could hunt seals. So I think they were getting something to eat, but they were quite hungry. It was shown by the fact they kept hanging round us.
You could show us just a little bit of it, maybe can you do a 5-minute extract of this film? Or
I haven't got it.
Yes,
It's
it's
not
not-
on you. I haven't got it on.
I've got it. It will take a while to find.
yeah, maybe not then.
No, and also it's finding the right 5 minutes.
Yeah,
But
time's getting on.
but the best thing might be another maybe
Yes.
next term we could actually do a show and
Well,
tell.
it'll be a
of
different
the
audience
film.
if it's next term, but
It is online. It is on iPad.
it is online. That's the thing.
It is on. So if you go to BBC and you type in Operation Iceberg, there's 2 episodes. The first one is about the birth of an iceberg which is covering the
Coffee
breaking off
in
from a
the
glacier.
afternoon.
Could be,
You
yeah.
in here.
We could do.
And the second episode is
Yeah.
the part we were on.
What about that this afternoon at 4 o'clock, say, here in this room? Well, there's no seminar over there. It's been cancelled.
Yes, well, maybe Till could show it, because I've got a meeting with the university lawyers, so it's going to be a nasty afternoon.
If
We'll
there's
just check
interest,
out that the room is available at 4 o'clock.
if there's interest,
But that's a good time, is it?
you've got the
Uh,
DVD, right? You've got it somewhere.
yes, 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 I have. Yeah, I could give you the DVD, or it's also on my computer. I think.
Okay,
But-
cool.
but-
Yeah,
Yeah.
no
Very
problem.
good. Very good.
So Till could
Okay,
show that.
well, thank you very much. That's extremely interesting. The program does make this point, but it's probably a buoyancy effect that's cracking it. You had 2 weak points, and I could see where the weak point at the bottom, the sort of tension tending to form a crack. At the top, it would seem more like compression.
Yeah, well, there's a whole load of the sort of fracture toughness work that was done on sea ice, and showing it's because ice has got virtually no strength in tension, but a lot of strength in compression. So it is more likely to be the tension
Yeah.
that would do it. But we can't really be sure till we've done some analysis properly.
Any questions? Oh, yes, please.
Sorry, philosophical questions. In conventional material science, microscopical property, structure, phase transition, extremely important for mechanics and stability. And in this business, whether such kind of investigations, there are many polymorphic structures of ice and water, such whether it's interesting and done. Or
Well, yes. I mean, our own interest here was in the distribution of stresses and the breakup mechanism for ice flows, and with respect to modelling the marginal ice zone. So we all the work we've done on the wave, the dynamics of the marginal ice zone involve waves entering the ice edge, being scattered by existing flows, and then causing flows to break up into smaller flows and giving you in the end a kind of equilibrium. And that's really important for the question of the role of the marginal ice zone in stripping away ice.
I think the question is, do you really need to know the physical
Oh.
properties of the ice?
Yes, you do. Yeah,
The elastic constants and that sort of thing.
yes, that's the problem, because
Yeah.
we were developing it for this sea ice application.
Uh,
We saw the giant tabular iceberg as the end member of all floating tabular elastic rafts. But the problem is it's a different kind of ice. I mean, it's solid ice, pure. It's pure ice, polycrystalline ice. While the other stuff is sea ice, which where the properties depend on its salinity as well as its temperature and so on. Whereas this ice is in a sense simpler, but still not simple. So you're right that you need to have really careful measurements and a good understanding of the ice properties to be able to really solve this sort of question.
Well, this is a problem where fluid mechanics meets solid mechanics in a most
Yes.
interesting way.
It's solid state oceanography.
Yeah. It's got so many aspects to it, thermal physics and everything else, and double diffusive convection, as you pointed out. Fascinating areas. Okay, well, wonderful. So we all know what to do with our summer vacation next year. It's exciting.
Just get onto the BBC and they'll happily take you out.
there. Thank you very much.